know there's an assignment due today, and I've got even better news for you. Today being tonight, and I've got even better news for you. The better news is that we have the second part of that assignment coming out today as well. In fact, it came out today. It's on Blackboard, and it's actually also, it should be in the GitHub if you don't have access to Blackboard for some reason. If you don't have access to the Blackboard for some reason, let me know, please, and we'll try to fix that. Okay, hang on, let me just try to get this system working. Now on. Okay, so wanted to talk about some logistical stuff, some housekeeping stuff, because I'm waiting for my projector to start up. Okay, if I just heard somebody say I haven't started it yet, that worries me, because it's really good. I hope you're talking about another class. A couple things. A2 Part 1 is due tonight. A2 Part 2 is out now and will be due in 8 days. And A2 Part 2 is hard, so they're going to have to kind of crank it back down and spend some time. But hopefully now that you've been warmed up on A2 Part 1, you're good. Let me quickly overview what A2 Part 2 is, and it should not be a shock now that we've talked about padding oracles like 3 times or twice in this class. But the basic idea is I want you guys to go out and implement one. You already have code that implements the encryption and decryption functions for this specific thing, or you will by 11:59 tonight. You have an implementation of an encryption and a decryption utility. And so what I want you guys to do now is I'm going to say, imagine you have access to a utility, which is very much like your existing utility. I'll call it test deck. I don't know if I called it that in the system. And this thing takes a ciphertext as input, and it has inside of it hard-coded key for the actual encryption scheme. You can imagine it could just output the decryption of the ciphertext, and that would be really easy for you guys, but I don't want this to be easy. Instead, it's going to output one of 3 possible messages. Can you guys guess what the 3 possible messages might be based on what you just did in this first assignment? Yes?
Padding error, tag error, and all good.
Good. Invalid MAC, invalid padding, or success. And so you guys are actually going to have to write this test deck program, but that should be really easy for you because you already have code for doing decryption. So just generate a random key, put it inside of this test deck thing, and it will take, I gave you the spec for exactly how it's supposed to run, and it'll take a ciphertext file as input, and it will output either success or bad, not exactly this, but it's in the assignment, bad MAC or bad padding. Okay, and your goal, your mission, should you choose to accept it, is now to write another program. I don't know what I'm going to call it, but we'll call it deck. And this program will call this other program, test deck, on the command line. It will take as input a ciphertext, but it will not have access to the key. And at the end of this whole mess, it should be able to output the decrypted plaintext, ciphertext under K, by the way. Okay? And so hopefully, now that you guys have seen all this, this is really straightforward for you, but this is it. So basically, we are hoping that there's a vulnerability in this encryption scheme that lets you do this. Yes?
So if we're going to use the same ciphertext on the output file, wouldn't that include the MAC and padding? So it's always going to be correct?
If this program takes as input a ciphertext and passes that ciphertext to test deck, you're absolutely right. If this is a correctly generated, honest ciphertext, which it should be, then that program will always output success. The problem is you're not going to learn very much about that plain text if you just do that. So the assumption is this program here is going to take a ciphertext as input, do something to it to generate a slightly different ciphertext, and it's that ciphertext which it's going to send to test deck. And it may do that many, many times. And by getting back, doing that many times with different versions of that ciphertext and looking at these errors, the assumption is that at the end of this, you will somehow be able to actually fully decrypt every bit of the original ciphertext. Clear? Okay, we've gone over padding oracle text. Feel free to come to office hours and talk more if this doesn't make sense to you, but This should be, at this point, I hope, pretty straightforward. So this is your testing program, this is your doing program, and it will hopefully be able just to call on the command line lots and lots of times. In previous years, we've done a version of this assignment that involved a web server, and then what happened was, like, inevitably the web server was too slow and everyone got mad at me. So I'm just trying to take out the middleman here and make things easier. Okay? A couple of things. There's a new reading, which unfortunately I haven't put up on the syllabus, but I'm going to put up on the Piazza and the syllabus after class. It's a paper, a survey paper by Dan Bonet called like 20 years of attacks or developments on the RSA crypto system. Since we're going to start talking about RSA, I want you guys to read that, and you can read that by next week. I will put it up and post it later. Important housekeeping stuff. Late day policy update. So I told you that aside from A1, after A1, I was going to give you guys a collection of 3 late days total, which you can spread out over the course as you see fit. When you do that, if you turn something in a day late, please, 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 at the top of your README or your assignment or whatever, indicate I used up this many days from my bank, and so we know that, and like we will know it's not actually late. If you are not able to get things in and you're not able to use your late days, then we are going to be really aggressive about discounting the value of the assignment. I had a big argument with my TA about this. He wanted this to be even worse, and so this is the nice. So we're actually going to take off 25% percentage points of your grade per day. That's not 25% of your final grade. That's like 25% of like 100 per late day. Yes.
Are those late days quantized by hours, or is it just
yes.
you have one day?
Good question. So yes, we will quantize them by hours.
Okay, cool.
Or we will not go below the unit of the hour, but we will quantize it by
Okay,
hour.
so
if
it's
you're an hour
72
late,
hours.
you're going to lose a few points, but you're not going to lose 25. We're not going to do that. So this works out to like about 4% per hour. Please don't be late. Okay. Good. What else? Okay, that's almost it. I think there was one other housekeeping thing. Why did that just do that? What does that even mean? Oh yeah. So we are going to have a final project in this class, and that's a pretty open-ended thing. What I want you guys to do today is start looking around you and identify people you might want to work with, because these are sort of group projects. 2 people, maybe 3 people if it's a compelling project. On Wednesday, I'm going to post a list of proposed projects to the GitHub, and I'll tell you about it, and we can talk these over. And what I want you to do after that is start thinking about things that interest you and your group, and like try to come to me, and we'll have a sign-up process where you guys can actually agree to do this. And this is just the preliminary stuff. You don't really have to start until after the midterm, but like this is kind of the preliminary. Let's get moving. Okay? Any questions about that? Good. Any news? Yeah.
There's a macOS High Sierra password leak, pretty much, where you could install an application on the OS and then get a plain text dump of all the passwords in the integrated keychain.
Oh wow. Okay.
And it was, I think, the person who discovered it told Apple about a month ago, and he had to publicly like leave the flaw yesterday because they hadn't fixed it.
Ooh, that's pretty bad. Did they say it was not a bug, or did they just not fix it?
They said that users got a warning when they installed an app that wasn't through the Apple Store, and so that technically covered it.
Okay. So what's a keychain? Somebody quickly tell me. What's its purpose?
It stores passwords so you don't have to remember them and enter them multiple
Good.
times, and other pieces of information.
Good. It can store keys, it can store certificates, private keys, whatever you want. It can all be stored there. And the idea is that, generally speaking, apps should not be able to just like pull everything they want from the keychain. How do you prevent an app from getting everything from the keychain? What would you do as a designer to limit what an app can get? Because they have to get their own keys and passwords sometimes, right?
You give an app a key, and it can use that key that key to encrypt the passwords that it wants to store, but you give a different key to every app.
Good. Okay, so what you can do is you can implement basically what you're talking about using crypto is some kind of per application like segregation, where you say like application A can't look at applications B's keys. And maybe you have some sort of shared keys, but this kind of gives you a really sensible thing. And I think, I'm not positive, that this is what Apple meant to do. When you download an app from their app store, it's in a sandbox, and I think the limitation is that app can only access things from the keychain that it created or that belonged to it. Whereas apparently there is this problem that if you download an app outside of the store, it could just like completely get everything from your keychain, which sounds really terrible. And so this kind of thing needs to be fixed. Now, just as a bonus question, if you use an iPhone, do you have a keychain on that?
It depends.
Okay,
It depends on whether or not you enable it.
okay,
There's the iCloud one, which is hooked up to your account, and that one is shared across all of your devices.
good,
So
okay.
there's that keychain, but that's optional to use.
Right, so there is a keychain that is like just a local keychain, just like on Mac OS, where you can write things to the keychain. They could be encrypted, and you can even set them to encrypt using like Touch ID, so that like you can't access them unless somebody is logged into the phone. So you can do all that stuff. But you mentioned this thing called iCloud keychain. That sounds really terrible. What is that?
Everything is synced between your accounts. Your Mac keychain is synced to your iPhone keychain.
Right, but not like, it doesn't go to your Mac, it goes to somewhere. And where is somewhere?
Data center.
The cloud, right, so big Apple server in the sky that like keeps all of your passwords and your keys. Should that scare you? Should you enable iCloud keychain? Does that freak you out?
Yeah.
Okay, can Apple, if Apple wants to, can they access all of your passwords?
Yes.
You think so? Anyone disagree?
It's end-to-end encrypted.
Ah, but okay, good. So this is the general speaking answer. People say, ah, we'll end-to-end encrypt this stuff, but with what? Yeah.
Well, basically, if it's in the cloud and you're using it, it can't be encrypted, can it?
It's kind of, well, I mean, what do you mean by using it, right? Like, if it's in the cloud, you can encrypt stuff and send it off to the cloud. If the cloud is just storage, I can encrypt a file, send it up to the cloud, and then it'd be encrypted there. That would work okay. And then when I download,
There's computation.
right? But is there computation over your backed up passwords? Hopefully not. So in this one case, I think you might be okay. Yes.
You can't.
Why not?
Apple doesn't store any information about your keychain with the servers. They don't hold the keys to your keychain.
Ah, how do they do that? So where are the keys to my keychain?
In the secure enclave, if
Oh.
you're using a phone.
This sounds really good. Okay, so what you're suggesting is that my passwords get encrypted with a key that is stored in a chip on my phone. Okay, so it's end-to-end encrypted. My passwords are encrypted. Apple can't see them. And the key to decrypt them is stored on my phone. Good. Only problem with that proposal is what happens when I drop my phone in the pool. Do I lose my passwords? This is a backup system, guys. You can't encrypt something with a key that only lives on the phone that I'm going to leave in the taxi, for which I need the backup system to protect me. So where's the key going to live if I lose my phone?
I thought it was secured with your iCloud password.
Good. Okay, so what's your iCloud password?
It's just like a password you have.
Oh, I
for
thought you
your
were going to tell me your iCloud password. What is, okay, it's a password that people type into a phone using the crummy little keyboard on your thing. Good, so we can derive a key from a password. We talked about PBKDF2, I think, a couple weeks ago. We can have your password entered. You can encrypt that key using your iCloud password. And now, as long as you don't forget your iCloud password, you're set, right? Does this work? Is this good? Are we set?
Someone can steal your password.
Someone could steal your password. Let's leave stealing your password out of our threat model, because then you're just screwed. All right, so what else? Yes?
You say you forgot your password.
Ah, okay, so first of all, possible vulnerability one is human beings forget passwords all the time. When you multiply that by Apple, which has 1 billion devices, that ends up being a big problem. So maybe they have a way to bypass the password, but if it's encrypted with your password, then presumably Apple can't do that. So let's assume we did that. Are we golden? Are we set? We encrypt things with someone's password, we derive a key from their password, encrypt their keychain stuff, send it up to the cloud, and now when the FBI comes in with a search warrant or criminals break into Apple, your data is really safe. How many of you guys use a high entropy password? How many of you guys even know what I'm talking about? How many of you guys use a really strong password? Really strong? Like 50, 60 bits worth of security strong? Okay, I'm actually going to give you numbers. 128 bits worth of security strong? Even he put down his hand.
About 100 characters long for this stuff.
100? How do you type that in?
Would you like to know?
Copy paste.
I don't use passwords. I use passphrases
Okay. I still think
that
that's
are easy for human beings to remember and hard for a machine to brute force.
Okay, well, maybe that has high entropy. We're not sure. We're going to hold off, and we're going to, with reserve judgment. Okay.
Okay.
The fact of the matter is when you're Apple, 99% of your users are going to use the password cat. And if you tell them you can't use the password cat, they're going to use the password C4T. And when you tell them you can't use that, they're going to use C4T exclamation mark, and so on. So the vast majority of users use crappy passwords. If you derive keys from crappy passwords, well, we talked about dictionary attacks. These are very efficient. And then we talked about ways you could try to make that a little better, like using expensive hash functions to derive keys. That slows things down a little. We tried memory. But it doesn't help you if the person uses the password cat. You're just screwed. So I would say that Apple kind of has a problem. They want to do end-to-end encryption. They could force people to use really hard to remember passwords, in which case everyone's going to hate them because they're always going to be losing their passwords and data. Or they can let people use simple passwords. Now I'm going to tell you one other thing. The password they use to encrypt at Apple is actually your PIN that you enter on your phone, which for most people is a 6-digit or 4-digit PIN. Is that secure?
No.
Nobody even here even thinks that it's a possibility that would be secure. No matter how much we crank things up, it would just be broken. Okay. So does Apple have access to your data? Your passwords, your encrypted passwords. Now I'm getting nods.
Encrypted? Yes.
Yes. No, do they have access to the actual passwords? With that 6-digit PIN or 4-digit PIN, can they get it?
Yes.
Okay, what if I told you no? That they claim they can't access it? Seems like we've got a kind of fundamental problem here. I've said that people are using weak passwords, but Apple claims that even with a weak password, they can't access your iCloud keychain data. Yes?
Well, they can't access it because it is protected.
No,
but
they claim that even, they have a very, very low probability, even being sophisticated, of decrypting that data. Any ideas what they might be doing? One of these days I'm going to make you read the iOS security policy or security guide or whatever, and you guys will figure this out. But the answer is that Apple has taken a shortcut, and the shortcut that they've taken is they use hardware. They use a device, which we'll talk about a little more in this class later, called an HSM, which stands for Hardware Security Module. This is basically a special purpose computer that you can program, and it has secure storage inside of it. It's hardened, so you can't like drill it open without destroying it. You can't get inside of it. It's supposed to be very, very secure. When you encrypt your stuff, what your phone does, is it actually encrypts your password directly up to this HSM, your short 6-digit PIN number. When you try to recover your passwords, you enter that PIN number goes to this HSM and checks it, and only then will it reveal, and it also stores a key for all of your data. And the idea is that Apple, they can program this HSM once, but they can never reprogram it. So the idea is that if this HSM is really doing what it's supposed to do, then Apple can't crack it open and open up their users' keys. The only way they could get their users' keys or data is to actually send the right password to this device. This device would check to see that that matches the password you sent it, and then it would give you back the key. And so since these passwords aren't very long, there's only maybe 10,000 or 1 million of them or something like that, they actually make this device keep a counter of how many bad passcode attempts you enter, and if it goes above 10, what happens? You destroy that person's keys. So Apple has actually made a really strong bid to try to make these things really end-to-end encrypted in the sense that they can't even access the data without the passcode.
This will be not enabled by default. The format places.
The iCloud keychain? Yeah, it's not enabled by default. You have to turn it on. And the reason is that once you turn this on, literally Apple has no way to get your data back if you forget your passcode. There's no backup system for this. Because the whole theory of this is that Apple can't recover data from that hardware security module. They can't cheat. The only way they can get data is entering a password. Yeah?
So then how did like back a year or so ago, the San Bernardino shooting, they recovered the password from that phone?
Chances are they cloned the phone using Cellbrite and then just tried 1 million times.
Yeah, so that phone had some weaknesses. It didn't have a hardware device, didn't have a secure enclave processor in it. Chances are somebody found a vulnerability and it was a 4-digit password. So once you get past all that stuff, they were just able to like use the phone to brute force guess 10,000 passwords. But what that vulnerability is, we don't know. Yeah.
Couldn't you technically disable the counter, like the keep account on that machine?
How? How do you do it?
That was what they were asking Apple to do for the FBI, was to patch the firmware in such a way that it didn't have that counter, and that was one of the things that they refused to do.
Yeah. So the obvious vulnerability here is if Apple could write new software and update the software on this computer, they could just update it to disable the counter. And these computers, they have, the way you update the software is with these access cards. That's the only way you can always reflash the thing and just wipe out all the passwords it stores. But if you want to update the software without wiping out all the data, you need these access cards, which are smart cards with data with special keys on them. And Apple has a special irreversible hash function that they use on these smart cards to make sure they can have, this is what they call it, a one-way function. And the function is literally they put them in a blender, and they, on video, destroyed all the smart cards, which means that Apple can never reprogram, they claim, this HSM. If they legitimately destroyed the smart cards, they had to get all of their code correct the first time they programmed this, because they can't fix any bugs that crop up in this without wiping out everyone's data. And so that's the kind of risk you take when you build things like this. Sorry, that's a long digression from news. What other news is there out in the world? Anything else going on? Nothing? Quiet week? Equifax not up to anything bad? Like nobody's doing anything terrible out there? Okay, well, we'll save news for next time. Today we're going to talk a bit about public key crypto, and I know Alicia kind of gave you an intro to some of this stuff. We're going to review it, and then we're going to move on. But before I do that, I kind of realized that we've been talking about symmetric encryption. We've talked so far, and before we move on to just pure public key crypto, we talked about MACs, and we've talked about encryption schemes. We've missed one thing, or at least we haven't really formally defined it, and that is this notion of hash functions. I know I've mentioned them a couple of times in different contexts, but I've never really gotten very specific. Can somebody quickly give me a definition of what a hash function is? It doesn't have to be a crypto definition. They're used in other areas of CS too. Yeah.
A one-time non-reversible digest.
Okay, digest. Let's start with digest. Okay, so a hash function typically takes in some usually variable length message. They don't have to be variable length, but we like it when they are. And they produce what is usually a short-ish fixed length output. And oftentimes you will see this referred to as a digest, because it's kind of like you take in the message, you digest it down into this like short thing that stands in place of the original message. Okay, and you said a bunch of other stuff too, but I want you to hold that stuff. Before we cared too much about cryptographic hash functions, what did we use hash functions for?
Passwords.
Okay, before we cared about passwords, what did we use hash functions for? Yeah.
Hash tables.
Good, and what's a hash table?
It's a way of efficiently storing anything. Like you don't have, if you want to store a really complicated object, you pass it through a hash function and put it in a hash table, and you get amortized O1 lookups.
Good, very good. Okay, so it's a very efficient way to take a complex data structure, arbitrary string, and you reduce it down into a digest, and then you have this very short digest you can look up when you want to find that thing again, or when you want to do a lookup in a hash function. What is the property that you need for a good for a normal hash table, non-cryptographic? Well, you go ahead, yeah.
Collision resistant.
Does it need to be collision resistant? Okay, do you want a hash function where everything maps to the number 0?
No.
Okay, there was this IOTA thing recently where actually you could find collisions like very easily, and that was really bad. But these things don't need to be collision resistant. They need to be something collision though. You don't want them to easily have lots of collisions, because then your hash table gets really inefficient, because lots of different things will have the same hash and your lookups won't be fast. So what is the property you actually want?
Low probability of collision.
Yes, on what kind of data? Is the data, are these things you're throwing in the hash table, are they generated adversarially, or are they generated just by normal processes?
Normal process.
Good, so for typical data, hash functions should not collide with very high probability. Ideally, they kind of work like checksums. They just need to work like checksums in the sense that you could probably spend a lot of time finding collisions if you're a bad guy, and that would make your hash table very inefficient. But why would you want to make your own hash table very inefficient? Okay, so normal hash tables, we don't worry about adversarial behavior. We just want an efficient function that produces a short digest that we can operate on. Okay, but cryptographic hash functions, of course, do have additional features. And we've been talking about this notion of collision resistance. Can somebody formally define what that means? Formally-ish define.